Hello and welcome to this lecture on quantitative data analysis. After this lecture, students should be able to define univariate, bivariate, and multivariate analyses, describe how quantitative data is processed, analyzed, and presented, interpret measures of center and measures of variation, explain elaboration, and interpret cross-tabulations and frequency distributions. Before data analysis can begin, we first need to be able to do what is called data modification. This includes editing, coding, entering, and cleaning. Editing is usually done with paper and pencil surveys where we need to make sure that the answers are legible and understandable, but also may need to happen in computer surveys and other forms of data collection where we need to double check what respondents have put down. We also then need to code or assign numbers or symbols to variables in order to prepare for data entry onto a computer. For any sort of nominal or ordinal level measurements, we need to be able to assign a numerical value to those categories so that the computer can read those entries. Next, we need to enter this data into a data matrix or a spreadsheet on a computer so that the computer can analyze it. And finally, we need to go through this matrix looking for and detecting and finally resolving any errors that might have occurred during this process. The first type of analysis we're going to look at is called univariate analysis. This is the next step typically in data processing. This is where we look at one variable and provide some in-depth information on each variable in our data set and any potential issues we might have with this data set. How we do this is going to differ depending on whether we have nominal or ordinal level data versus interval or ratio level data. So here is an example of univariate analysis using nominal or ordinal level data. And this typically takes the form of a frequency or percentage distribution. Here we have both. So here we have a nominal level measurement that is marital status. And we have categories here that include married, widowed, divorced, separated, and never married. This second column here is the frequencies. And we can see how many people in our sample fall into each category. So we have 1,158 people who are married, 209 that are widowed, and 411 that are divorced, so on and so forth. Of that, we can also get what is called a valid percent. This is the percentage of cases that fall into each category minus the missing cases. So we're going to ignore this percent column and focus just on this valid percent. And so we can see that 45.7% of our sample are married, 3.2% are separated, and 26.6% are never married. And then finally we have this cumulative percent here which adds up each of these categories. So for married it's going to still be 45.7%. For widowed we're going to add the percentage of people who are married plus the percent of people who are widowed so that we get 53.9% that are widowed or married, 70.2% that are divorced, widowed, or married, 73.4% that are separated, divorced, widowed, or married, so on and so forth. And so when we're looking at nominal and ordinal level data, we're going to be using this sort of frequency and percentage distribution to see what our data looks like, to see what each category in our data set looks like. So when we have nominal and ordinal level data, we're going to use these frequency and percentage distributions to get an idea of what our data for that variable looks like. How many people or what percentage of people fall into each category. How evenly or unevenly distributed are our cases. For interval and ratio level data, our descriptive statistics are going to include things like mean, median, mode, range, variance, and standard deviation. So here we have a table that looks at scores on English, reading, and math and writing tests. And we can see that we have N here is the number of people for each of these scores. We have the minimum, so that's the lowest grade or lowest score for each of these. The maximum or the highest score for each of these. The mean, which is the average, taking each score from each individual person, adding them up and dividing by the total number of scores. And the standard deviation, which is a measure of how far apart our data is. So the mean here is a measure of center. It measures how close together our data is. whereas the standard deviation is a measure of spread. It measures how far apart our data is. So what this means is that the English average score was an 82.72 with a standard deviation of 6.82, which means that most of our scores are going to be anywhere from between 75 to about an 88. And that'll include close to about 70% of our scores are between those values. Once we have processed and done our preliminary univariate analysis, we can proceed to an analysis with two variables. This is where we start getting into an independent and dependent variable. Like univariate statistics, bivariate statistics, looking at two variables, is going to look different if we're using nominal or ordinal level data versus interval or ratio level data. Bivariate analysis also looks for what we call statistical significance. This is usually defined as a 0.05, 0.01, or 0.001 and corresponds to a 95% confidence level, a 99% confidence level, or at a 99.9% confidence level. So if I say a 0.05, think 95% confidence level, 0.01 is a 99% confidence level, and a 0.001 is a 99.9% confidence level. And these 0.05, 0.01, or 0.001 reflect the probability that when we say it looks like our independent variable is causing the change we see to our dependent variable, that we are wrong. This is called type 1 error. When we say, oh, it looks like our independent variable is the cause of our dependent variable, and we are wrong, that is going to be type 1 error. And so what we do when we test for statistical significance is we see if the relationship that we have between our independent and dependent variable, does it fall below this 0.05, 0.01, or 0.001? If it falls below these values, if our probability of being wrong falls below these values, then we can be pretty sure that independent variable is causing the change we see to our dependent variable, or if it falls below, say, 0.001, we can be 99.9% confident that the independent variable is causing the change we see to our dependent variable. So here's an example of a bivariate analysis using nominal and ordinal level data. Specifically, this is an example of what we call a cross-tabulation or bivariate table. So here we have a table. We have one variable which is class rank, which is ordinal. We have freshman, sophomore, junior, senior, so categories that we can put in order. And we have a nominal level measurement over here, which is do you live on campus, or off campus. And here we can start to see a relationship possibly between your rank in school and whether or not you live on or off campus. These areas outlined in red are what we call marginal frequencies, and it's the totals in each variable category. So this 137 represents all the freshmen, this 90 represents all the sophomores, 98 represents the juniors, 63 seniors, 231 people live off campus, and 157 live on campus, for a total students of 388. In the middle here, we have the cell frequencies. So this 37 represents the freshmen who live off campus. 100 here represents the freshmen who live on campus. This 42 represents the sophomores who live off campus, and this 48 represents the sophomores who live on campus, so on and so forth. While this bivariate table is useful, it doesn't actually tell us a statistical significance. To get that statistical significance, to see if there's actually a relationship between living on and off campus and your rank in school, we'd have to do what are called chi-square tests, measures of association, or measures of correlation. The chi-square test for independence tests to see if the distribution of cases in the cells is random or patterned. Basically, do these variables look like they're just randomly sorted into these cells? Or is there a pattern to it such that it seems like there's a relationship between living on or off campus and your rank in school? However, the chi-square test only tells us if there's a pattern or not. It doesn't tell us the direction or how strong that relationship is. And in order to get that information, we have to either do a measure of association or a measure of correlation. Measures of association measure the strength of a relationship between 0 and 1, with 0 being perfectly random, no relationship, not at all strong, and 1 being a perfect relationship or perfect association, which would be a very strong relationship between living on or off campus, and your class rank. Measures of correlation also are measured between 0 and 1, but they also include a negative and positive. So with measures of correlation, we can measure the direction. Measures of association only look at the strength, while measures of correlation look at strength and direction. A positive value means that the change in the independent variable will cause the dependent variable to change in the same direction, while a negative sign, a value below 0, between 0 and -1, means that the change in the independent variable will cause the dependent variable to change in the opposite direction. Looking at bivariate relationships between interval and ratio level measurement, we're going to be using what is called bivariate regression. This is the effect of one interval or ratio level variable on another. And we do this typically by creating what we call a scatter plot, where we plot out all the data that we have, all the different cases, and find a regression line or best fit line that minimizes the sum of the squared distance from the mean. So we're going to take this best fit line and we're going to find all the values of these differences here between each point and the line and square them and add them up. And that's going to be how good our line fits our information. And we square it because if we truly have a best fit line, then if we just added up all these values and their differences between our cases and our line, we would get 0. So what we can do with this bivariate regression is we can start to predict scores. So we have a slope. Anytime we have a line, we have a slope, also called b. It is also known as the regression coefficient, and it is how much y changes for every unit change in x. We also have a y-intercept. This is where the regression line crosses the vertical axis, or where x is going to be equal to 0. This is also known as a constant. And so what we can do is we can create a formula called y equals a plus b times x. In this case, y is going to be our final score, x is going to be our hours studied, b is going to be the slope, so how much one unit change in x affects y, and a is going to be the value of y when x is equal to 0. And what we get is we get a formula that says y equals 30 plus 2 times x. We get the 2 because when we go from 5 to 10 hours studied, the score increases by 10. So for a 5 unit change in hours studied, scores go up by 10. And if you remember back to your algebra in middle school or high school, the slope is going to be rise over run. So we have 10 increase in final score divided by a 5 increase in hours studied is going to give us 2. So for every hour studied, you would expect your score to increase by 2. We get 30 because when x is equal to 0, so when we decrease 5 from 5, we go 5 minus 5, we get to 0, we can see that our line will go down to here and we'll have 30. So if you studied 0 hours, you would score 30 on the exam. So we get a formula here that is y equals 30 plus 2 times x. And so we can start to predict what people's scores would be if they studied for, say, 3 hours. Because we can say y equals 30 plus 2 times 3, again, 3 being hours studied, and we get a value of 36. So we can say that if you studied for 3 hours for your exam, we would predict that you'd get around a 36% on the exam. But we can do this with others as well. Say you studied for 20 hours. We can say, well, y equal 30 plus 2 times 20. We'd predict that you'd get around a 70. So we can use this best fit line to then predict what your score should be if this line is correct. However, it's unusual that we only have one independent variable and one dependent variable. With a bivariate regression, we only have 2 variables. But generally, it's important to include other variables, either other control variables or other independent variables, that more accurately model causation. This process of adding these control variables is called elaboration, and again, our goal here is to accurately model causation. It's very unlikely that the only thing affecting your score or your grade in a class is the time you spent studying. There's other things, like how much sleep you got. Did you eat breakfast? Did you study throughout the semester? Did you attend class regularly? All these things are going to affect your grade on the exam, not just the amount of time you spent studying. And so what we want to do with multivariate regression, more than two variables, is we want to, as accurately as possible, model all the things that could be causing a change in your final score. And we determine how well a causal relationship is modeled by how well it controls for those extraneous variables. Things like amount of sleep, did your car break down on the way, class attendance, all those sorts of things that we can control for and include in our multivariate regression means that we're going to have a better model of what causes you to get the final score that you get. And leaving out important variables in a regression can lead to what is called specification error, where we are not accurately modeling the causal relationship between our independent variable and our dependent variable. Alrighty, that's all for this lecture. Thank you for watching.